So here's the entire machine, built out of 80/20. The doors are salvaged off of some industrial equipment. And the whole thing, these panels are all 1-inch high-density polystyrene foam, which is aluminum faced. You get it at Home Depot or Lowe's, the home improvement stores. And that's on the left and the right side, the back, the top, and there'll be one underneath the bed as well to insulate the entire machine. So the bed is made up of 4 mix 6 or cast aluminum tool plates. They're 1/4 of an inch thick, and each section of the bed has 2 400 millimeter square silicone heating mats. So I went with this design versus something different, such as a single mat or 2 larger mats, mostly for servicing the machine. If I have a mat die, like this one per se, I want to be able to just replace this panel and not have to tear apart the entire printer more than just removing the glass bed and one section. So in theory, you could pull this 1 quadrant heater out, put a new one in, service this one offline, and keep it as a spare. Whereas I had got prices for 900 millimeter square heaters, 2 of them, but the risk was just too high for me. If one failed, you could be down for weeks while waiting for another heater, plus you have to delaminate that heater from the bed, relaminate the new one, all kinds of trouble there. So this made the most sense in my mind. So these are 220 volt heaters. I will be running 4 quadrants. And these will be running off of solid state, heatsink cooled solid state relays to modulate them, as well as regulate their power usage so that way they don't draw as much as they're capable of. So the plan is to use the PWM of the heaters, or the solid state relays, to modulate the heaters to regulate their power consumption, and we'll probably do some kind of off-board control from the Duet to regulate the heaters themselves. Probably a staging control, so we're not running all 4 heaters at the same time. We'll rapidly switch each section on and off to distribute the power load, and then we can apply more power to 2 panels at a time, or one quadrant at a time, but rapidly, maybe 10 times a second or so, cycle between all 4 quadrants, so we don't have to run a 50 amp circuit. We can get away with only a 20 amp circuit. So this will be insulated as well underneath the heaters, and not shown, there is 3 crossbars that are 2 inches square supporting the heaters, as well as some more supports on the edges supporting the edges of the plates. So on top of the plate there is a 1/4 inch sheet of tempered glass. This was very reasonably priced in my opinion. I got a price of a little less than $200, custom cut, edges smooth, corners rounded, and brought into the local glass company, and then for a small fee they'll deliver this to my house, and I might be able to even get them put it right in the machine. But I figured for $20-30 to have them delivered to the house was a lot better than risking damaging the plate, transporting it in the pickup truck, since I don't have the equipment to transport glass like they do. So that's the structure of the bed. We'll move up from there now. So the doors are polycarbonate, or Lexan. I have these they're not going to be the most insulated. I will most likely look into adding a second layer of polycarbonate to create an airspace later on, so I don't stress the heaters too much. I do have a 2400 watt resistive heater fan coil unit that I'll be using to heat the chamber. That'll also be modulated through a solid state relay. So let's turn off the enclosure so you can see the workings of the machine. So you'll notice I'm supporting it on 4 screws. So these are 1605 ball screws. The price was right on these. That's why I went with these. I would have liked to go with 1604s, but I just could not get them. And I would have gone with 1204 ball screws, but also couldn't get them in the length I wanted. So while I have the capability of machining all these parts custom, I didn't want to. I didn't want to waste all the time building a machine when I really just wanted a printer. So some compromises. There's a lot of concerns out there that these screws are not the straightest screw. So I did some tests. I tested 2 out of the 4 screws that I bought. They all came at the same time from the same distributor. I put them on a known flat surface, and I checked them with an indicator with the ball nut at the center of the screw, and I was getting about 1.5 thousandths of run out on the center of the screw to the nut. So in my mind, that was good enough for me. Like I said before, I'm not building a printer that is for crazy high accuracy. It is for putting down a lot of material in very large layer widths that shouldn't matter if the screw wobbles a few thousandths of an inch. So there's a few things here that aren't drawn yet because I don't exactly know how they're going to work, and I'm going to have to figure them out on the fly. But for the most part, this is the printer. So 4 screws, we have stepper motors. We'll jump into the model for them. So these are basically all the same. We have a 25 millimeter dual profile THK linear rail. This is something I've salvaged from some machinery over the years. I actually have 3 sections of rail. One of them is long enough to get 2 out of, and the other 2 are long enough to get 1 apiece out of. So these are cut at 33 inches roughly in length. And then I've designed these upper bearing supports in these lower brackets, and these reuse the bearings that come with the screws. So it was actually cheaper to buy the ball screws with the end bearings and just reuse the pieces out of it than it was to try to do something else. So what we have is the angular contact bearings that are in a mount, and that it just gets put into this housing, which is 3D printed for now, but if that's not sufficient, we'll move over to machining these. That was always the goal. And then the same with the upper mount, which just has the single bearing pressed into the mount. So these bolt onto the 80-20 extrusions. They have cutouts in them to locate the linear rails, so you don't have to worry about aligning those. They just bolt the bearing blocks to the machine, slip the rail down into the channel, slip the top bearing on, you slide onto the screw, slide onto the rail, drop a bolt in here, another bolt up through there. There we go. So the ball screw attaches to the linear rail bearing using this mount that I designed. So this is just a mix of this cool design, this spherical mount for the Voron, and I extended that out on this little arm to mount the screw. The screw lower the nut, and then that bolts to the bearing, making it all one assembly. So down here, we've got a NEMA 17 stepper motor, and that is coupled to the screw. We have a 16 tooth pulley, GT2 6mm wide timing pulley to a 60 tooth GT2 pulley, and a little tensioning mechanism, which, yep, we do have it. There's a bearing, or two bearings, and there's a little screw here, so you just adjust the screw to tension the belt. The belts are snug to begin with, but this is just to give it a little bit extra on it. So we jump back to the main model. So we have 4 of those, 1 in each corner. There's a left hand and a right hand version. They're just mirrors of each other. And those will form the Z-axis. So it is a rigid Z-axis. In theory, you could get some flex out of the gantry with this, but it wasn't primarily designed for that. The primary goal was mesh bed leveling, taking care of it. The reason why I had looked into and designed, spent weeks designing, a kinematic mount system using 3 screws, one here, another one over here, and then a third one at the back. And it was a kinematic mount system, which would allow the entire gantry to go off of plane. But then I realized that if there's any deflection in the x-axis gantry beam, that can't compensate for that, and only mesh bed leveling can. So I figured if we have to use mesh bed leveling to compensate for sag in the gantry, we might as well just use it for everything. So that's how I decided about the 4 rigid points. So the Voron design. I love the Voron printer, and I plan to build one eventually as a smaller printer. My printer I have currently is a phenomenal machine. It's my workhorse. I never have trouble with it. I load a part, I hit print, I get the part I wanted. So I started with the Voron design mainly because it was already done. All of the geometry for the belts was laid out properly. None of that would have to be recalculated. So I just set about modifying for what I needed. So this is what I come up with. Well, the Voron is great for a high production, high quality, fast printer. It's expensive to start. The Voron runs between $1,200 and $1,500 if you're careful to build one of the larger size ones. This is the Voron 2.4 specifically. I'm not terribly familiar with the other models. But that's all using linear rails. The problem with a printer this size is we're over 1700 millimeters in X. And to try to get linear rails, 9mm linear rails of that size, is extremely difficult. So then you're looking at splicing rails. Not the greatest option. Just not many good options to try to put linear rails of this size onto a printer this big. And I didn't really want to. I didn't want to spend half as much on 3 linear rails as I did on the entire printer. So, with the whole resolution and quality in mind, I decided to go with this. So, just like your run-of-the-mill extrusion-based V-rail printer, I used V-rollers. So, with this, this is a hybrid of, which is, if you notice the name, This is a hybrid of the Voron 2.4 rail and the Voron, not rail, sorry, carriage, as well as the Voron 1.8 carriage. They are very similar. All the holes line up, the idlers line up. So I took those and I modified them to work with V rollers and a larger beam for the cross beam. So this stuff is all metric. So this is 2020 V-rail, similar to open builds. And then the cross beam drawn here is 2040. However, I'll actually be going with a 2020 V-rail for the rolling rail, and then a 2040 in a vertical orientation bolted to the 2020. I need to redraw that. And that'll give me vertical stiffness for deflection, and the 2020 will be my actual rolling structure. So with this, I can replace these rollers hundreds of times as they wear without worrying about the cost of putting linear rails on a machine this size. So this machine has currently 9 V rollers, 1 on this 3 on this carriage, 3 on the other side, and 3 on the carriage that traverses. Here we go. 3 on the carriage that traverses with the extruder head. So right now this just has the Voron afterburner extruder drawn on it. I haven't drawn the Titan yet. So even if I replace these every print, you're not talking more than $10, which we're talking hundreds of dollars of filament per print. So the cost makes sense. The wheels are a consumable in my mind. So this design, I have removed a lot of the holes on the drives just for strength, and I'm still in process of updating the other drive. I don't know, is this the B? This is the A drive. I still have to finish updating the A drive because in my testing, this corner structure is kind of weak. So this is still using the 6mm belts. Like I said, I'm trying this as cheap as possible, and we'll upgrade from there. So the first idea of upgrade is bigger belts. So right now this will have 6mm belts on it. We can upgrade to 10mm belts. It's just printing some new parts, use the same rails, and we'll go with bigger belts. Will also be some belt supports in thirds. So there'll be one roughly here and another one roughly over here. And that will help with the belts just whipping as they traverse back and forth. So some of the other stuff not shown, there'll be a plate bolted to the outside edge of the y-axis rails here. I'm not sure if that'll be steel or aluminum, but that'll be just bolted to the rail just to provide additional vertical support like a spine without impeding the V-rails for the rollers. And that's so that this can span this distance, what are we at, 900 millimeters, without sagging under the weight of the x-axis gantry. As this is drawn, this is upside down. It actually goes in the printer like this. And you may have noticed that in the main printer drawing, but that is so that the stepper motors can clear the bed. So when this thing is all the way down, like that, Without the stepper motors being on the top side, we can't get the head close enough to the bed. So this most likely won't be an issue with the Super Volcano, but if I wanted to put a secondary tool head or tertiary tool head with something like a V6 so that I can do high resolution printing with like a 0.4 nozzle instead of a 1.0 nozzle, I need to be able to get it close enough to the bed to actually do that. So that's the plan for that. So that's roughly the plan of the printer. Now, a couple of the other small details. Feeding a printer like this. So this printer is going to go through many kilograms of plastic per print. So we have to have a continuous feeding mechanism. While you can get rolls of filament that are 3, 4, 5, even up to 10 kilograms of plastic, while that stuff is very common in PLA and PETG, it's getting there, not as much in ABS and ASA that I'm looking to print.